Whenever you log into a website, send an email, or make an online purchase, you're counting on your data being sent securely without hackers being able to crack the code. But in the coming decades, powerful quantum computers will likely be able to break many of the security systems that we depend on today. Cryptographers are using a wide range of mathematical tools to develop new methods that can withstand even the most sophisticated quantum computer. Welcome to another mathematical moment from the American Mathematical Society. I'm Scott Hirschberger. Today we're talking with Dr. Angela Robinson, a mathematician in the Cryptographic Technology Group at the National Institute of Standards and Technology. She's part of the NIST post-quantum cryptography standardization process. It's a competition to develop the most promising techniques for sending and receiving messages securely in the quantum era. So, Dr. Robinson, thank you for joining me. I'd like to start with sort of the big picture context of the problem that we're trying to solve with cryptography in general, and then especially post-quantum cryptography. So can you tell us a little bit about what the basic idea of a crypto system is?
Sure. So one of the big problems that cryptography attempts to address is privacy, also authenticating yourself, and ways to do this in our digital world these days. So as you mentioned, encryption is definitely a key component of that. This allows us to send emails, messages, chats, things across public channels in a way that eavesdroppers wouldn't be able to understand what message was sent without some underlying secret key. You also want to be able to authenticate yourself. Think about when you're communicating with your bank. You need to digitally sign a form. This is it's like the analogous to a handwritten signature, but now digital signatures based on cryptographic techniques allow us to do that without, actually having to sign paper.
Okay, that makes sense. So the algorithms that we use now to encrypt all our data, why are they vulnerable to quantum computers? Like, why do we need to design new algorithms?
That's a good question. So the encryption schemes used today are included in standards documents. So NIST has standards. There are other standardization bodies across the world that choose to standardize certain algorithms because they've been tested. All of the specific parameters have been analyzed and they're deemed secure up to a certain point. So some of the schemes, well, actually, all of the schemes in the NIST public key encryption standards are based on underlying math problems that can be broken by a quantum computer. One example of this problem is integer factorization. So if I say 35, that's a simple integer that we can factor in our minds, 5 times 7. Well, it turns out when you're working with much, much larger integers, say 1,000 digit integer, that's only a product of two prime numbers. This is something that has been shown to be difficult for our classical computers to solve. And for that reason, there are encryption schemes, namely the RSA encryption scheme, that's based on this problem. So essentially, if you are capable of factoring this large integer, you can then break the encryption scheme. Other examples are encryption schemes based on the discrete logarithm problem. And it turns out that there's a quantum algorithm called Shor's algorithm that can break the integer factorization problem and the discrete logarithm problem. So because that's what's in our standards, it's time for us to update our standards with new encryption schemes that aren't based on these two problems.
Okay. And so at NIST, you're working on this post-quantum cryptography standardization process. So can you talk a little bit about what that process entails, kind of where you are in the process and what your role is?
Because it is well known that what's included in the public key encryption standard is vulnerable to quantum attacks. NIST initiated this worldwide process. Some consider it a competition, but NIST doesn't consider it a competition. But essentially, NIST announced to the world that we're looking for new schemes to include in the standards that would be secure against a quantum computer or quantum attacks. And so NIST accepted proposals from all across the world. Initially, there were all sorts of proposals, and NIST began a process to sort of reduce the number of schemes under consideration with the goal of having just a few to be selected for standardization. So I joined NIST. I joined this project during the first round of the standardization process, and we looked at every single scheme, looked at what the community is saying about these schemes, the security, the performance. So one of the really tricky aspects of the job is that security is paramount, of course, but unfortunately, security is not the only thing that matters to the everyday user. It's not competitive if someone has the most secure product, but their product is very slow. If you had a smartphone and every time a software update came, it took 30 hours, you wouldn't want to use that smartphone anymore. So there's a big trade-off between security and performance. So we look at these things. It's definitely a group effort. So my part in the project is to focus on a small subset of the schemes, present it to the group, and we go from there.
And so earlier you talked about, for example, the factorization of very large numbers into prime factors in kind of the algorithms we're using now. Can you tell us a little bit about some of the math involved in these new algorithms that are being proposed?
Sure. So there are a couple different families of mathematical objects. The nice thing about the integer factorization problem is it's working with just integers. So some of the new schemes are working over different objects. So one would be an error correcting code. One would be problems involving lattices. So a lattice is simply like an evenly spaced grid of points you can think of on the XY axis. So the concept of a lattice is something that you can visualize, you can see. And this grid of points, they're evenly spread, and they're always defined by two basis vectors if you're working in 2 dimensions, like just the XY coordinate system. Well, just like with the integer factorization problem, the actual hard problem is not in the 2-dimension case, it's in much larger dimensions, which is something we can't really visualize. We can visualize 3 dimensions because now you're in the XYZ space. But over much larger dimensions, it's harder to visualize, but the problem is still the same. And the problem is lattices have many different ways that you can select the basis vectors that define the entire lattice. And one of the harder problems in larger dimensions is finding a short vector in the lattice. So if you have extremely long basis vectors, it might not be very obvious which vector is considered short within the lattice. And finding that short vector amounts to a means of creating some crypto system based on this hard problem.
So what is the timeline for the rest of the process and, for eventual implementation of these algorithms?
Another fantastic question. So we haven't set a final date for the end of standardization. We are hoping to have a first draft or some idea of a first draft or an idea of which schemes would be suitable for a first draft of a standard by 2023. But this isn't a hard and fast rule. The exciting thing about cryptography is that things are always improving, changing. While you have cryptographers trying to improve the security of a system, there's also cryptanalysis happening in parallel that's constantly trying to break a crypto system. So because of this ongoing academic battle, we never know what might come out. So if there's a major attack that breaks some of the schemes under consideration next year, that might affect our timeline and things like that.
Well, cool. Sounds like an exciting future for sure. And what do you enjoy most about working on this project, using your mathematical skills to work on cryptography?
I love a lot of things about this. One of the things that I really, really enjoy is just how much math is beneath the surface. I think it's really exciting because it shows there's always more to learn. So like I said before, some of the areas of math that were used the most was number theory. Well, now it's not just number theory. We've got coding theory, lattices, maps between elliptic curves. There's all sorts of things to study. Another thing that I do enjoy is bringing awareness to all of the cryptography that we're using every day in our daily digital lives. When I have friends or family that ask, what do you work on? I'm able to point out to them, the security that's behind all of these secure websites. And the algorithms have names, and it's fun to be able to explain what these algorithms are, the mathematicians who designed them. So it's very exciting times.
Very exciting indeed. Well, thank you so much, Angela, for talking with me. This has been fascinating. Dr. Angela Robinson is part of the NIST post-quantum cryptography standardization process. She's a mathematician in the Cryptographic Technology Group. And you can find out more about her work in the related resources over in the description or on the webpage that you're looking at. So thank you so much.
Thank you.